Okay, so now I'm going to talk about naming ethers, but this time I'm going to talk about naming ether, giving them IUPAC names, which I think is a little more difficult. So I've broken naming up into common naming lecture and IUPAC naming lecture, so you could easily access which one you need. I know I did this in the other one, I just don't know what order people are watching this in, so let's go as soon as my mouse will work. So remember, ethers are organic compounds in which an oxygen atom is bonded to two carbon atoms. So we always have this. So we think of it as two R groups here. So the way we're going to name, so the ether functional group is right here. And so the way we're going to name ethers by IUPAC names is maybe a little, it's a much different way of thinking than when you do it by common names. So you just have to kind of forget the common names. We're not going to think of these in the same way at all. Instead, like we always do in any compound, we're going to find the longest chain of carbons. No matter where it is, it's not actually going to include the oxygen. So somewhere over inside one of these R groups, there's going to be a longest chain. In fact, one of the R groups, along with the oxygen, is going to be considered a substituent, like this. So let me give it a direct example. Because once you start thinking about these in terms of common names, the IUPAC name seems a little strange. But it's just like we've always done. Just have to kind of forget about the common names. So imagine I've got oxygen. Actually, let's just do a simple one. And I kind of drew it silly for it to be a simple one. So let's do like diethyl ether, like that. Now what we're going to do is we're going to try to find the longest chain of carbons. Now the thing about this longest chain of carbons is it's not going to actually involve the oxygen atom at all. But it does have to involve a carbon that is directly attached to the oxygen. So that has to be either this one or this one has to be part of the chain. Now it turns out either way we go, they're the same length. We can either make a 2-carbon chain here or a two-carbon chain there. Oops, sorry, I'm chasing weird things. Okay, so let's just pick one. Let me redraw the structure again. So I'm just going to pick this one as my longest chain. Now, we start numbering nearest the carbon that has the oxygen bonded to it. So it might help if I drew the same thing this way. So I'm going to do this. Now this is going to be carbon 1, this will be carbon 2. So 1, 2, like that. Now what I'm going to do is, so that's my 2-carbon chain. So this is the parent name, just like any other time we've ever done this. It's going to be ethane. Now what happens is we have to identify that as a substituent, and that substituent is on carbon number 1. So it's attached to carbon number 1 here, so that's where the 1 is coming from. It's attached to the ethane chain at carbon number 1. This is a substituent. And the name of the substituent, so imagine that I had a substituent that looked like this. It had just two carbons on it. We'd call that an ethyl group, right? But if it's got an oxygen stuck between it and the parent chain, we actually change the name of it. So let me erase some of this. So if this, here's my parent chain, if this is an ethyl group, then this is an ethoxy group. So eth still coming from the 2 carbons here, and oxy coming from the oxygen. Let me draw that in a different way. Parent chain. Here's an ethyl group. Oxygen. It's basically an oxygen with an ethyl group on it. So an oxygen with an ethyl group on it is collectively called an ethoxy group, which is what we have here. So this becomes 1-ethoxy, and there shouldn't be a space. I just left too much space here. Let me rewrite the whole thing. So it's going to be 1-ethoxyethane, right there, 1-ethoxyethane. So no matter how that shows up, we have to look for the longest chain. And so the oxygen may not be bonded to the longest, it may not be bonded to the first carbon in the chain. So if I had something like this, right, my longest carbon chain is actually right here, right? So what we call this, so now we start numbering. Now I'm going to number closest to the alkoxy group. So an OR, that's called an alkoxy group as a general. So alkane oxy is where that's coming from. So this I'm going to number on the longest chain closest to the end with the alkoxy group substituent. So 1, 2, 3, 4. So that means my alkoxy group is on carbon number 2. This alkoxy group in particular is called propoxy. So this becomes 2-propoxy, propane, oxygen, and then this parent chain is butane. Right? So we're just treating the oxygen with the R group after it as just all one substituent. So 2-propoxy butane is what this gets called. Let's do another one. So let's do another one. Let's do O. Okay. This looks really complicated and scary, but we're going to think about it in terms of how we would always name it. So what's my longest chain or my biggest chain or the thing I would normally use as a parent? Right, the cyclo, the ring. So this becomes, the parent name is cyclohexane. Now I'm not going to throw these at you during an exam. I just want to show you that how this works. I'm using this as an example to show how generalizable this idea is. So don't expect this to come out of an exam. Just follow and understand what I'm doing. So this is my parent chain. This now is the alkane substituent. So what we do is we just take whatever the substituent name would be, and then we put oxy on the end. So this group, if you look at it, is an isopropyl group. So the whole group here in blue becomes, actually I should have done that in red to really show that I'm showing the red one. So isopropyl, and the whole group in blue becomes isopropoxy. And then all we have to do is, actually we don't, I just realized we don't have to indicate where it is. Because the number in front of isopropoxy, I think this is where some confusion comes in. It doesn't have anything to do with the attachment over here. The attachment over here is not what we're talking about. If I put a 1 here, I'm indicating where on this chain the isopropoxy group is attached to the parent chain. So the parent chain is a cyclohexane, and remember, when we only have one substituent on the cyclohexane, we only have to put a single number indicating where it is. Or we don't have to put any numbers because it's assumed to be at carbon number 1. Let's do another one. Okay, so this one looks really big and nasty. Same thing as always. We're going to find the longest carbon chain. So if we look over here on the right, this is only 4 carbons long. So 1, 2, 3, 4. Over here on the left, I kind of drew it differently. I should probably draw it so they all look the same. Let's do it this way. Uh-oh, I have no idea what's trying to happen now. Okay, so my longest chain is actually, take a moment and see if you can find it. I want to pause it. My longest chain is actually right here. Remember? So don't make the mistake of thinking that the carbon that the oxygen is attached to has to be the first carbon in the chain. It's not necessarily going to be carbon 1. We're going to indicate what carbon the oxygen is attached to with a number. So don't assume that you have to start at number 1. That is only for the common name and for the oxy substituent. For the parent chain, you can start wherever the oxygen can be attached to any number. So we have to look at all the substituents. So this is exactly like naming anything else. Don't get overwhelmed by the fact that it's an ether. We find the longest chain. We're going to number. Well, pretty clearly we have to number from here. 1, 2, 3, 4, 5. Now, we look at all of our substituents. So the parent chain is going to be pentane, and that's going to be the parent name. Now, let's look at my substituents. I've got a 2-methyl group, so dimethyl, and the numbers will be 3, 3. They're both attached at the 3rd carbon. And then we have this butoxy group. Actually, I'm going to do this way in black, and so I'll write it in black. Butoxy. It's a butoxy because it's 4 carbons long and it's got an oxygen here. So it's a butoxy group. Should draw it that way. And it's attached to the parent chain in red at carbon number 2. So what we get, and we have to put these in alphabetical order. Again, we ignore the di, so we look at B versus M. So it becomes 2-butoxy, 3,3-dimethyl pentane. So we only really use these methoxy group designations, this IUPAC naming, for big, complicated, weird-looking ethers. Most of the time we're going to use the common names, but sometimes they just don't work. I mean, how would you name this whole thing in the common names? It would be a big, gnarly name anyway. We'd have to put in parentheses, and it just becomes a pain. So this is the kind of structure we name in using IUPAC rules. So I will indicate on an exam or quiz whether you have to give me a common name or an IUPAC name. Don't worry about having to determine that. I will tell you. Just make sure you're able to do both.